Hello, everyone. My name is Vincent Salucci. I'm a program maker for the TU Delft Library. I'm in charge of the exhibitions and cultural programming here. We've had the distinct pleasure of having a large program with some international collaborators this spring, and this is the SHErobots program, which was put on in collaboration with the universities of Sydney and New South Wales. And we have the exhibition over on the other side of the library. If you haven't had a chance to check it out, I encourage you to do so. It highlights over 27 female researchers and female-led robotics research team, and representing 8 different countries. So it's a little bit design-centric, and one of the things that we wanted to do to broaden the conversation and bring more of the TU expertise into play is to have a side program, and we call this the SHErobots Cafés, which you're attending, I believe, the 7th of 8. So we've invited female researchers in robotics at the TU Delft, and we've grouped them into themes, and we have a nice lunch. And also, one of my major goals for this program was to get as many robots into the library as possible and to let people actually interact with them and experience them. So we're going to leave some time to do that. Basically, the agenda for today will be, we'll have 2 short talks. Then we'll have a small discussion panel, and we'll invite some of the researchers and the student assistants and younger colleague researchers to join us in a small discussion. We'll open that up for audience participation and have some questions. Then we'll adjourn and actually play with the robots in the demos. So that's the plan. And I'd like to formally introduce our speakers. So I'll go ahead with that so we can get to the talks. Our first speaker will be Katherine Poggensee, and she is a postdoctoral researcher in cognitive robotics at TU Delft and the Department of Rehabilitation Medicine at Erasmus MC. She studies methods to improve human-robot performance for rehabilitation and assistive robots through motor learning and optimization techniques. She completed her PhD in mechanical engineering at Stanford, focusing on ankle exoskeletism for walking assistance. And her fellow researcher that we'll be presenting is Laura Marchal Crespo, who's an associate professor at the Department of Cognitive Robotics in the Mechanical Engineering faculty. She is also affiliated with the ARTORG Center for Biomedical Engineering Research from Bern, Switzerland. She carries out research in the general areas of human-machine interfaces and biological learning, and specifically in the use of robotic assistance and virtual reality to aid people in learning motor tasks and rehabilitate after neurological injuries. So let's get right into it with our speakers, and we'll have some fun today.
Great. Thank you, Vincent. Oh, that's working. Great. Okay. Well, thank you, everyone, for showing up. I hope you're all enjoying your food. Today, I'm just going to give an overview of the different types of robots that exist for research functions, assistance, and rehabilitation. There are lots of different use cases for this, but I'm going to focus my talk today on walking. So walking is something that most of us can do without thinking. We can walk while texting, drinking a cup of coffee, or holding a conversation, sometimes all 3 at the same time. But for some people, locomotion is not quite a walk in the park. Nearly 10% of adults in the Netherlands have mobility limitations, and this only gets worse with the onset of old age or the onset of disease. Walking can also be challenging for people that have to walk a lot for their profession, like nurses. Assistive devices can facilitate that independent living. And while simple handheld devices, here a walker, a cane is another example, those are still the most prevalent in society. But there have been significant advancements in robotic technology that can offer more powerful, personalized assistance and also rehabilitation, all while freeing the hands. I'll first talk about exoskeletons and some of these other robots. So these devices in general are versatile, programmable, and often incredibly effective for a range of tasks from assistance to rehabilitation and then even research platforms that can give deeper insight into human motor control. So again, I'm going to give a brief overview of the different devices that I've worked with, but this is just a sampling. There are many more examples of these different types of devices. So this talk is structured into 3 distinct areas. Robots as a research platform to yield greater insights into human motor control, robots for assistance, in particular to aid mobility, and also for rehabilitation. But as you'll see throughout this talk, these devices kind of blend into all of these other areas. So it just depends on whatever task you're interested in. I want to first talk about exoskeletons as a research platform. So I might use some of these terms interchangeably here. An exoskeleton is what we would call a wearable robot. So some wearable devices that you might typically interact with are things like a smartwatch. Here, this is a robot. So it has all of the trappings of your typical robot where there's, a brain and actuation and things like that. You can tell, though, that this is just a prototype. So what you can see from this picture is that there's a lot of duct tape. It's not particularly streamlined, and the motors and control are actually at the back of the system, and so the person cannot leave the treadmill. This, while it seems like a design flaw, is actually a feature. This was intentionally done to make this a more adaptable system. This in particular is something that we call a universal device emulator. So these emulators allow the user to experience a wide range of devices without the need to design and refit new specialized hardware. So we can try out a wide variety of these designs while allowing measurements of the human response in days, minutes, rather than years of development. And so the idea here is to first identify what functionalities are needed to have success with the human users, and then we can take those ideas and then embody them into specialized, specific hardware. The devices that I'll show here are focused on prosthetics and exoskeletons, but you can imagine how these devices can be applied to a wide variety of movements. This emulator system goes hand in hand with a specific control algorithm to identify, we have the hardware, how do we control it so that it best augments or assists or rehabs the user. So we used something called human-in-the-loop optimization. The main idea here is to put the human in the loop of the optimization. So we can tweak the control and maybe some design aspects of the robot to immediately improve human performance. Specifically, we can take a controller. So these exoskeletons give you a little oomph on every step when you walk. So every time you take a step, it gives you a little oomph to push off your foot. So if you think of that oomph and how we can parameterize that control, you can parameterize it both as we give you some amount of assistance. We don't know how much to give you, so we need to figure that out. And then also when that assistance should be applied. So that's 2 parameters and infinitely many combinations to try. So we need to find a way to quickly identify which pair is best. For this algorithm, we can take a set of candidate parameters or values. These are all sampled around what we consider our best guess. We have some idea for the amount and timing that you'll need, but we don't know exactly what's the best. So we can sample all around this space to get a finer estimate of what works for you. We then apply these controllers to the person to see how they perform. And we can measure that performance directly. So here we use something called metabolic energy. This is just the energy that it takes your body to perform these tasks. This is a typical outcome used in walking research. There are lots of questions that can come up with that. Feel free to ask them during the panel. But once you have these measurements, you can then rank all of the different pairs. So once you have this ranking, it'll give you some idea of what your next best guess should be. And then you can use that next best guess to sample around and try to refine that guess even more. So this loop of optimization is called generation. And for people who understand optimization, you can go through many iterations of this to get more steps towards your best guess of what the best assistance should be. This works much better than hand tuning. It allows people to spend a lot of time practicing using the device, and it gets you to the answer much more quickly. And it has been shown to be more effective than typical hand tuning practices. With this study in particular, we were able to double the energy, more than double the energy savings just by using this algorithm. So we can apply these ideas to our system to see how people interact with this assistance. A key finding, which might not seem obvious, is that we were able to show that people can actually walk with assistance. So for people who haven't tried an exoskeleton before, think about putting on high heels for the first time, or ski boots. It's clunky, it's awkward to walk in. You have to figure out, you feel like a baby, you're figuring out how to walk again. And in particular with this device, when people put it on, they said, quote, turning on the assistance is weird and it can make you feel ridiculous, but eventually people get used to it. I'll replay that as well. So in this study, we had people walk for 6 days in order to get fully used to the device. Previous studies showed that it only took you like 10 minutes to just put on the device and you're able to walk out the door, but we showed that it takes at least 2 hours of walking before you feel truly comfortable using this assistance. So this gives, it's not just a way to find what types of devices and assistants can help a person, but it actually gives us a lot of insight into how important motor adaptation is to interacting with these robots. So using these two ideas in parallel, we can use exoskeletons to understand human movement. So using the exoskeleton, we can ask questions like, can we make walking take less energy? For people who have studied walking research, and you're all going to think about this as you leave the room, we naturally tune our step width, our step frequency, such that we take the least amount of energy. And so we're already incredibly efficient. Can we make people more efficient? And we've shown that we are able to with exoskeletons. We can also make running take less energy, same principle. And we can also enable people to walk faster. So instead of using energy cost as our optimization cost function, we can actually try to increase the speed. And we've shown that people were able to statistically significantly walk faster using this hardware and algorithm. Again, we can understand how important motor learning is in these human-robot interactions. And we can also see how these interactions change with different populations. For example, we can put an exoskeleton on a person with amputation to give more insight into why maybe if we have these robotic prosthetic feet, they haven't been shown to be as effective. Potentially, it's not a matter of the prosthetic hardware not being good enough. It might be a sensory deficit that was lost when you lost that limb. So this is a brief overview of exoskeletons for research, but they can also be used for assistance. This is an extension of our ankle exoskeleton hardware. As you can see, there are more motors, so you can control more degrees of freedom. Here, this controls the hips, knees, and ankles. And while this gives you a lot more power, we're able to reduce the energy cost of walking by half. But with those extra parameters, the optimization gets much harder. You get to the point where you can no longer algebraically solve for any specific value sets that you want. And these devices in particular, you can think of them more for augmentation. So these can be used in military applications, for example, to help soldiers walk farther, faster, longer, et cetera. And if we want to think about assistance devices, then we can think about this in terms of smaller wearable devices that you can just go out into the world and it can assist you throughout your daily life. And for this, we'll actually look at a different type of actuator. This was created at the TU in combination with Demo. So these are gyroscopic actuators to assist your balance. So very quick summary of what gyroscopes are in case anyone needs a refresher. If you remember from your intro physics classes, if you have a spinning wheel and then you rotate that spinning wheel, it'll generate a torque. And so we can harness that idea to apply these torques to a person's trunk to give them a little bit of extra assistance so that they can more easily balance themselves using their trunk movement. So in an older version of this device, we were able to apply this gyroscopic actuation to assist people in balance. So this device is on the order of like 15 to 20 kilograms, but you can see that when the device is inactive, it's just this heavy weight. We put people in a difficult balancing task, walking along a beam, and they're not very good at it. But when we apply some amount of assistance, you can see the device is moving, and they're able to walk much farther. One of the ideas that's also encoded in these videos is that for some of these assistance studies, it's a little bit difficult to test them in healthy populations because, again, we're really efficient, we're really good at moving, so we have to make the task more difficult, which is why we had people walk along the beam. But this is probably not our target population, so how does this work on patient populations? So here we have one person who has had a stroke, and they're standing on the balance beam. You can see that when the device is turned off, it's very difficult for them to maintain balance. But when we turn on the device, they're able to stand a little bit more steadily, and they're able to stand for longer. This device appeared to be effective, but again, it was really big, and so not the type of thing that you want to walk around spar with. So for this, we actually developed a smaller, more compact package, and we did these same types of tests where we had people walk along a beam and stand on the beam. We also had a few more tests, so you can look at the paper if you're interested. But these studies showed that with this small amount of assistance, so this is more on the 4 to 6 kilogram range, with this small amount of assistance, we were able to improve balance in a number of different measures. For example, people were able to walk further along the beam, and there was maybe less erratic movement of their trunk. And so, again, with the same cycle of testing this in healthy populations and then testing this in the patient populations that would most benefit, we have a recent collaboration with people at Radboud University where we were able to bring this backpack for people with ataxia who have difficulty balancing in general. So in a placebo condition, you can see that there's a lot of movement. He's not able to stand for very long. But when we apply assistance, it almost looks like he has full support. He is standing perfectly still. As you can see, the time is progressing. I'm not going to play the whole video because he stands for too long for this presentation. But with this small amount of assistance, we're able to see major benefits in how these different patient populations could move about the world. And then finally, I want to talk about rehabilitation robots. So these are the types of devices that are built similarly, but you can't take home. These are the devices that if you were to go to the clinic, they can put you in this device, you can get a lot of training, and then you go home. And hopefully some of that training kind of rubs off on you. The difference between assistance and rehabilitation is that assistance will be with you for the rest of your life, and rehabilitation is to empower you to be able to make those physiological and motor control changes so that you're able to move without the device. This is our Locomat. You can see it if you come to the cognitive robotics department. So this device, I don't have a video for this, but the idea is therapists often when they're training walking will move your legs for you. You can see here, this is where a therapist would normally be moving those legs. But we could actually have a robot do it instead of the person. While this is great in theory, there are lots of other questions that we need to ask. This is a very powerful system. It's nice because it can support some of the body weight, but it could potentially support too much of the body weight. So we have to figure out a way that enables people to create those motor pathways so that they can do this movement on their own while still giving them some level of support or maybe a little bit of resistance training or something so that they're able to do this motion when they leave the lab. And this is a classical example of this robot that can rehabilitate walking, but it's very big, very expensive, and so you actually don't need robots to get this similar idea and similar type of rehabilitation. You can use more passive devices to help with foot placement. So it's the same idea of trying to get people to place their feet correctly. So in this system, we have cables, and one leg drives the other leg's movement. And so this simple mechanical design can also achieve some of the same goals as these big robotic devices. So this was a very brief overview of all of the different types of devices that we have in our group that can assist, rehabilitate, and help us understand how people move. Laura is going to speak more on the upper limb devices that can help you, that can assist you and rehabilitate you and stuff. But this is just a brief overview, and I'm happy to take any questions during the panel. And before Laura comes up here and switches over a laptop, I just want to thank everyone who took part in this research, and thank you all for listening.
Looks like we're good. If you go to the full screen. Yep. Yep.
Good, thank you very much, Katie. I think that your talk was very good for me to transition to start mine. My name is Laura Marchal Crespo, Associate Professor here at TU Delft. And today I would like to talk about our journey towards meaningful robotic rehabilitation. I will be focusing mostly into the upper extremities, since you got everything from Katie about the lower extremities. But before we start the talk, I would like to do an exercise of empathy altogether. So imagine that you, Imagine that you wake up one day and you go to the kitchen in order to be able to have your first cup of coffee after a long night doing your exercises or reviewing homework. And when you want to reach and grasp your cup of coffee, you can not move your arm. This is weak, your hand is cramped, and you cannot open your hand, even if you put all your mental effort into it. So this is the reality of half of the 15 million of stroke survivors every year. So think about it. 1 in 4 adults will suffer from a stroke in our lifetime. Luckily, our brain is capable of reorganizing its structure, allowing for the recovery of the lost function. The question is, how can we maximize this recovery? Neuroscience evidence says that in order to enhance the function after a stroke, you have to engage in high-intensity and task-specific training. This is very labor-intensive, and you need a therapist all the time helping you to perform this task. I'm the head of the Motor Learning and Rehabilitation Lab. We are an interdisciplinary group of engineers, industrial designers, movement scientists that co-create together with clinical personnel new solutions to support therapists in providing this high-intensity training. An example of technology is, for example, Armin. That was a robot that was developed at ETH in Zurich when I was a postdoc over there. And with this robotic device, we can provide the support to perform complex arm movements. This is a very magnificent piece of engineering art. It's very complex, and yeah, it's a wonderful device. But as Katie said before, it also suffers from some limitations. The first one is that it's very bulky, it's very expensive, and it's not very usable. It really requires therapists to go through a process of understanding how to use the technology in order to be able to use it seamless with the patients into the clinics. Also, because it's expensive and bulky, you can only use it into the clinics. While with the aging population, we need to do a move towards rehabilitation at home, so patients can have even more high intensity with very low supervision. The second limitation is that usually what you see in therapy is that you have the patient that is performing 3D movements, and they only see a 2D representations of the movement in a screen somewhere else. And this is very difficult to patients who also suffer from cognitive impairments to understand. Something that you do every day with your mouse and you see a cursor on the screen, for stroke patients, this is very difficult to grasp. The third limitation is that while they are interacting with these very engaging virtual reality games, they don't feel the objects they are interacting with. And this is quite a limitation because you need to get all this information that is coming from the skin and from the muscles in order to be able to skillfully manipulate these objects. So this training environment actually feels like this, like trying to teach people to swim outside of the water. So I guess that we all agree that this is not the ideal training environment because you need to feel and you need to see the water in order to master this skill. So how can we expect that the stroke patients regain functional movements if we don't provide them with realistic visual and somatic feedback? So in our group, what we are doing is creating this ideal environment by combining the robotic devices with head-mounted displays where you can see the virtual world in 3 dimensions. And at the same time, they are also able to see their own body moving. By doing so, we are reducing the cognitive load that we are putting in patients while playing with the games. Furthermore, this immersive virtual reality allows us to trick the brain of the people. And I love this part of my job, because you actually can make people believe that their body is made of, for example, different material by providing congruent touch and sound. Now you see, you hear as if you are touching a stone. You can make people really feel like their arm is made of a stone. And by doing so, they actually move faster because they overcompensate for the idea that actually they have to move a heavy object. And this is very cool. But we are here to talk about robots, so I'm going to put the virtual reality aside, and let's going to talk a little bit about all this feeling that we need in order to master these movements. So in order to be able to master movements that requires the feeling of forces, actually you need to get this information, what we call haptic rendering. We are using the motor of the devices to simulate the forces that you will feel when you are touching virtual objects. And we want to do this not only by augmenting our cool exoskeletons, but also moving towards the rehabilitation at home, simplifying the devices, and also reducing the cost in order to be able to have our robots located in the homes of all stroke survivors who need it. So in order to be able to do this, what we did was to spend many, many hours into the clinics, empathizing with the therapists and patients through the rehabilitation journey, from the screening, the first day, till their discharging. Only by doing so, we can understand the real needs and the real interest of the patients and therapists in order to develop our technology in a way that it's usable, and they accept it and use it. So after the first step of empathizing, it's very important to have the list of requirements that the new technology needs to have in order to meet the needs of the therapists and the patients. So what we did was to run an online survey with 33 participants, not only including therapists, but also nurses, physicians, and so on. And then we asked them to rank the importance of different movements that should be trained in order to maximize the rehabilitation of the hand. And what they told us is that they don't care that much about independent finger movements. They're interested more in training all the fingers at the same time. They were also interested in training the supination of the hand to do cylindrical grasp, that is the one that you use to grab your bottle, and also the independent thumb movement to put it in opposition to the fingers in order to be able to do the grasp movement. And they were less interested in all the independent finger movements. We also learned that they are not willing to spend more than 5 minutes setting the patient inside of the machine. So the arming was completely out of this game. So we further talked with the therapists in order to be able to have very clear requirements. So what we wanted to have is to have a new hand device that has to reduce complexity. So without the individual finger movements, that it's very easy to set up. So maybe it will be good to have a handle where you can slip your fist, because many patients also suffer from spasticity. They cannot open the hand. It's very stiff. So it's very difficult to open it to put a device in each one of the fingers. Also, it's very important to train extension movements in a full range of motion, from full flexion to full extension. Also should be suitable for different hand sizes. No complicated adjustments, so we can do everything in less than 5 minutes. So maybe it's better to have an exchangeable handle instead of changing the length of different links of the robots. And of course, we should be adding this haptic rendering in order to provide this somatic feedback back to the brain. So I'm very proud to show you the results. So by changing the handle, what you are doing is changing the size for each hand size, because this handle is locating optimally the position of your metacarpal joint here. Then you can slide your fist, and then only with 2 straps, you can secure the hand of the patient into the robot. You will be playing with it in a bit. So with only 1 motor, what we can do is to support the training of the full flexion to full extension in a very physiological way. So very sustainable solution. We augment our pride with a thumb model, also to meet the request of the therapist to have the thumb in a position. So with another 2 motors, we are able to support the position of the thumb in a position and also the flexion and extension of the fingertip. And we combine our robotic devices with very motivating games that you will be playing in a while, thanks to the support of the people in the lab. So we run experiments with patients in order to test the usability of our invention, and they were always by therapists and also by patients. They said that we found that they are between very good and excellent usable. So they were very much looking forward to welcome the technology into the clinic. So while our technology was very accepted by the therapists, we wanted to even do another step because we want to go to the homes. This is still too big to go to the home. So what we did was to continue our journey into designing more portable devices. So this is our portable sensory motor hand training. We need to find a more cool name at some point of our life. So it's very easy setup, and it's very intuitive. Everybody knows how to grasp it. It supports the opening and the closing of the fingers, and so also the thumb. It also allows for a passive degree of freedom of the supination movement that the therapists were asking for, and it's super easy to change the size of the shell. That it's the novelty of the device. So it's not with movable things. So everything is a 3D printed shell. So actually it's inherently safe. And then we combine the robotic device with different games where we are leveraging on the feelings. So you will see it, well, you feel it, that each one of these liquid dispensers feel different, has a different viscosity. And then the patient needs to provide the correct amount of forces in order to be able to fill each one of the glasses. So we also run usability tests with this portable device, where we use questionnaires to gather information about possible improvements, but also we combine it with other technologies, such as, for example, eye tracking, because we were interested to know where people were looking at while they were interacting with our robot. If they were maybe looking more into the robotic device, meaning that maybe it's not as intuitive as we thought, because they have to be all the time looking at it, or if maybe they were looking more into the emergency stop, because they don't feel safe. And what we saw actually is that they were never looking into the emergency stop. They hardly look into the robot, and they were very engaged into the game, always looking into the areas they should fixate in order to be able to fulfill the task. So this is our journey so far, but Irene joined us in order to even make it more usable and even to make it more low cost. And this is her PhD that you will hear, because she will be part also of the panel, where she is researching into doing the technology even cheaper, even more usable, even more sustainable. And this is thanks to our Convergence Human Mobility Center. This is a program where we partner together with Erasmus Medical Center and Erasmus University, where we combine different disciplines like social science and medicine and engineering, and with also rehabilitation centers such as Rheindam and Lawrence. And we all together are working towards these tailored technological supports at home treatment. So everything from the clinic into the houses. So that was the talk of today. Just as a lesson learned list, and I would like to send it to you. Always when you are designing your technology, use a human-centered design, because otherwise you are risking that your technology is not going to be used by the final user. You really need to understand what is that they need in order to be able to provide them with what they want. Go for cheap, intuitive, and usable technology so you can democratize the technology instead of going for the fancy, sophisticated stuff that we love. Actually, our portable devices, the simpler they are, the more sophisticated they are inside. And finally, include all stakeholders. So till now, we could not interact that much with stroke patients because of legal and ethics, but this is something that we are trying to compensate with our Convergent flagship. And that was everything for today. Thank you very much for listening.
May I invite the rest of the panel up? Yeah. Please have a seat. Some water. I'm going to get the conversation flowing with a few questions, maybe, and then quickly turn it over to the audience for questions. So thank you for the talks, and I was curious, one of the first things that came in my mind is how, what your prediction is for this ubiquitous future where we have a robot in our every household like a blood pressure machine is now. Like how far away are we from this, do you think?
Actually, I believe that almost everybody has a robot in their house, because if there is a Roomba, right, or even with if you have children, right?
Well, an assistive one for healthcare purposes, maybe I should qualify.
Yeah, so I think that it's going to be the same process, right? So we also had to get used to the technology when it came to home to support us in activities of daily living, like washing your clothes. Yep. It's just that we need to understand how this technology is going to interact with the people. It can be very creepy. So we have to maximize the acceptance of the technology.
Absolutely, and feel free to grab a mic when you want. Yeah, this is a subject that's come up time and again with the SHErobots exhibition. In fact, one of the panels talks about how how intimate you're willing to get with a robot in your body, and in terms of and maybe even like allowing a robot to say care for an elderly parent or something like this. So these it seems like the bigger hurdles, not the technology, right?
Well, I think I'm not sure if it's working yet. So with the aging population, I think the technology is already within our population. So now the elderly might not be as comfortable with technology, but as we move on, technology is already around us all, and if we're old, we already know how to interact with technology. So in a couple of years, I think everyone is comfortable with it, or at least more comfortable than the current elderly population is.
Great. And speaking about the SHErobots and the themes, the subtitle of this exhibition is Ecologies of Care. And within the healthcare context, I think I've asked everyone this question, but within the healthcare context, it's a particularly obvious answer because the word's in there, but I'm curious how you view your research as an act of care, and maybe you could provide a little bit more of a personal anecdote or something to get away from maybe the obvious connection of healthcare being care contained within healthcare.
Katie?
I'm thinking of the care aspect, because much of the research that I've done is on the assistance and motor learning side of things, and so I haven't done quite as much in the healthcare aspect. But I think, I guess maybe one way to interpret this is by giving people agency. So rather than imposing some amount of care, the devices that I've worked with have given people the opportunity to explore how they interact with the devices, how they move throughout the world. So the motor learning experiment that I talked about, where we had people walk in exoskeletons for several hours, we gave no instructions, but full emotional support as they had to walk in these devices for 12 hours. And so it ends up, and this is again specific to the population. I was working with a population of young grad students in Silicon Valley, so they were very technology focused. But it ended up being more fun, and so it was less of a hassle to get them to actually engage with these devices. And this is something that we're thinking about as we develop these devices for the home. Not just can we have something sustainable, easy to use, but something that people actually want to use. And so we can't provide that care unless they actually take on the robot and interact with it.
Well, that reminds me about care and this usability within the world and increasing access. There's also some cultural things that come up with this, and I know that various countries like using the assistive walkers, for instance. In some cultures, this people might not feel so. Might feel ashamed using this walker in public or stuff like this, and I'm curious how this questions like that get approached with the research group, especially since we have people from various countries in this interdisciplinary research.
That's a good question. Actually, we have a whole, I'm laughing because Salvo is laughing, so we have a whole workshop in a conference coming up about all this topic. It's about embodied technology and how it really changed, so that we as engineers are not taking into account how people are going to feel when they are wearing it. So people may be pointing at them, right? Or they may feel powerless because there is something that is supporting them. This is true, but I don't feel powerless because I wear glasses, for example, right? I believe that in the moment that you realize that actually this is helping you, things change. And then you start accepting more the technology.
Well, especially if it increases your agency, right? So.
Yeah, correct. But nevertheless, it's important to take all these different points of view in consideration. And so one of the lines of research of our lab, for example, is looking into the personality traits of people who are using the technology, so we can adapt it to the personality of each person. Some people may not like to be supported by the robots, and Katie touched it a little bit. Some people prefer that the technology is challenging them. So you need to really understand the final user in order to be able to design for the final user. So going through all the process of personalization. Instead of designing technology that fits everybody, it's technology that is personalized for each specific personality type, each person, its specific desire, values of each person.
And I'm curious, related to that, because the program's also very much about gender, and is there any research that sort of says like, I don't know, maybe men, if you think about the stereotype, right, maybe men are cool with this big gadget mechanical thing right on their legs or something, but maybe women are not about, does this come up in any of the research? Or?
So yes, but I was actually thinking about, as we were, I've had too much experience with this now, as we've designed this hardware, for both upper and lower limbs, a lot of this research, and this is true for, even with cars and things like that, a lot of the research was done with men in mind. And so, for example, some of the hand trainers, we have been able to scale it down so it does fit. I have tiny hands, and so it needs to be able to fit, your typical larger Dutch man and also my tiny little hands. With the exoskeletons, they fit onto your body. So people have different body shapes. With the backpack, where do you put the straps such that they're able to apply that force without being uncomfortable to wear for many hours? So while there is a lot of importance in dealing with how people's different personality traits interact with the types of assistance and functionality they can get from these robots, we also have to take these other design choices into account. And so, as Laura said, one of the most important things that we need to think about when we're designing these devices and building these protocols to interact with the devices is to sample a very diverse population, because we're engineers. We think we know how people should interact with these robots, but we took the hand trainer to a science fair with children a couple weeks ago, and they were using the devices in totally different ways than we would have expected. And yeah, we're not children anymore, so we weren't able to expect that.
Very nice. And last question for me before turning it over to the audience. The SHErobots platform is also about mentoring, and we're fortunate enough to have several generations of medical robotics researchers here. Because maybe I can start with the younger researchers and talk a little bit about mentoring from in your experience.
Well, as I don't know if this is what you refer to, but I think these kind of mentoring things are really important because, for example, in my case, when I was in high school, I never considered doing an engineering because I didn't know anyone that would have done it unless a woman. So I think promoting this mainly in younger age, it's super important to engage them to this to really make an informative decision.
That's exactly what I'm referring to. But feel free to add more.
So I remember when I started my master's thesis, I was looking for research that I thought was interesting, and I came up a male professor, and I joined his team. I was the only female in the team of like 6, 7 people for 2 years. And every time like, oh, we need more females. But after me, I don't think there was any other female student joining on this particular topic. And there were times that like we did shoulder rehabilitation and we did motion capture, and I was like, yeah, but you cannot capture some of the EMG sensors with women because we're wearing bras, and where are you going to put them? So they never thought of it like, oh, it's easy, just bare top, it's fine. I'm like, I'm not going to go bare top doing this experiment. So yeah, it's very important to also include the female researcher in these type of research activities.
And maybe Katie and Laura maybe can speak to your own experience with mentors and colleagues.
I didn't have a female mentor. That it's very sad.
Trailblazer, then.
But it really creates a feeling of isolation. And I believe this is one of the reasons why I engage in this kind of activities, like the one that you are organizing, because I really believe on the power of this, of being a role model. I believe that the impact that you can have on the young or the future generation is huge, just by the fact that you exist and you go through all the process to become professor.
Great. Well, if there's anything that you could say to them, because we are putting this on YouTube, is if you have some solid gold advice for the students, the young female students watching this online.
Ooh, this is a difficult one. Do you have any advice? Well, I think about an advice. Yeah. It has to be only one.
I think it goes both ways. I have 2 brothers. My elder brother is in biomedical sciences, and when my younger brother had to choose his degree, he did also the technological high school program. And he felt forced to do engineering because he was good at physics, he was good at math. He ended up doing history, which is where he excels in. But it was a very tough choice, and he struggled telling my parents, like, I want to move into a different field, which is less common to expect from boys. So I think it goes both ways. My parents always knew that I was into technology, so it was not a weird step for me. But the other way around, it also exists.
Yeah, and I can build on that. So I lied when I said we're all engineers. I was not originally an engineer. I actually did movement science, so the study of people moving, biomechanics, and math. And so when I then did engineering in grad school, then it was just this horrifying realization that if I didn't pass this exam, then I was going to fail out of my PhD. And so I guess I would say you don't have to follow what you think is the straight line path towards whatever career you think you want, whatever that next step is, that sometimes it's okay to take these kind of side directions to get into whatever you want. By having this movement science background, it allows me to think about these problems in a different way by centering the human in these human-robot systems. That path also is not going to be straight because there are going to be many, many significant failures along the way. And so failure is always miserable, but if you get comfortable in that misery, then it makes your life a little bit easier, and you're able to more quickly adapt and learn from those mistakes.
Like the robots.
Yeah. Oh yes, we have so many failures with the robots. Happy to talk about this.
Okay, let me open it up to our audience. Any questions, burning questions?
So I've done a lot of volunteering in the rehab center of a nursing home. How do you think your designs over there for the upper limb robots would interact with people who might not be as tech literate?
That may not be, sorry?
As technologically literate. Like they wouldn't understand how to maybe interact as fluently with a computer interface.
Yeah. Yeah, so what we are doing is try to enhance the user interface. So one of the main problems that I believe that exist is that you have a robot with a lot of capabilities, right? And the user interface is so painful. I mean, even myself, after many years, sometimes it's difficult to understand what the user interface is asking me to do. So what we are trying to do is to solve this problem, make it much more intuitive. Understanding the language that the people who are going to use the robots speak, because this is one of the difficulties, is that actually we are not speaking the same language. We are in our wonderful world of technology, and they are in their world of therapy, and if we cannot understand each other, and we can understand the way they talk, we cannot have good interfaces that actually are communicating with the patients in their own, or with the therapists in their own language. So this is one thing, and reducing the time to set up the patient is fundamental. If you need to spend, so usually the duration of a rehabilitation session is around 45 minutes. If you have to spend 20 minutes setting the patient, basically you are cutting the therapy to only 20 minutes, right? Because you also have to remove the patient. So our solutions, you can put the patient inside in less than 5 minutes, so that you can maximize also the therapy, making the robot more usable, but also more acceptable, because you are not wasting the time of the patient. You are actually maximizing the potential of the rehabilitation.
For these devices that move the patient for them, how do you ensure that they don't move the patient past their range of motion or overpower them in a damaging way?
Yeah, that's in large part from the design and software stops. So we have hard stops and soft stops within these systems. Again, this is all created under the idea of like a young, healthy adult male. And so as designers, we slightly tweak these hard stops. So with the one device that I showed for the knee, we actually have it so that when your knee is fully extended, there is a physical piece that is in the way. So you hit that. With some of our other systems, we designed in small little mechanical brakes so that a rope would break before you would. And as engineers working with people, I mean, this is similar to like if you're doing civil engineering or something like that. If you're building a bridge, you don't want people to fall off the bridge. And so we put in a lot of factors of safety. There's a lot of prototyping, asking people to move in weird ways and testing with lots of different people to ensure safety.
Well, thank you. Hello. Yeah, thank you very much. Yeah, in 10 years, where would you want rehabilitation robotics to be at, and what are the most important things that have to happen to reach that state?
I think that we have to make the rehabilitation meaningful. So instead of providing tools, we need to provide experiences. So when I was pregnant with my first child, my mother-in-law had a stroke, and she nevertheless came to Switzerland to help me. And the first days before my child was born, she was not capable of doing anything, right? So she could not move the hands, she barely could do the dishes, although she really wanted to be useful. And when I was back from the hospital with my first child, and then she grabbed my child, stable, standing up, with so safe, so confident. And this is meaning. There was a meaning to the movement, right? And this meaning was what it was making her to be capable. And I believe that this is the way that, the journey that we should do to make the rehabilitation meaningful. Like you have all these exoskeletons, and now we have virtual reality. And if you have somebody who loves to walk on the beach, yes, create an environment that is able to replicate this so they can, again, feel and do what they really love. And then this is going to motivate them to keep doing it instead of being just attached to a robot that it's all the time moving them. So this is my feeling, and this is the vision of our lab, to provide these meaningful rehabilitation experiences.
Yeah, and I think not just motivating the patients and the participants, but also the healthcare system that enables these robots to be put into people's homes. So that's something that we're working on within our flagship, of finding better ways to communicate our technological advancements to the people that will actually be using these devices, promoting them, and trying to figure out a shared language that we can use.
Yeah.
Great question. We'll have one last one, and then make sure we can play with some robots.
Thanks a lot for these inspiring talks. I was wondering, because you already referred to this, so in the near future, rehabilitation has to go from a clinical setting to a home setting. So how would you see the role of the therapist?
This is a very good question, because they are going to actually change their role, right? They are going to move from being the ones who are providing the assistance to be the ones who are teaching the patients to use the tools. And we are seeing a lot of, we are seeing some opposition to this, because actually therapists have a lot of difficulties in seeing the future, or imagining the future. So we are trained to do this, right? To try to have our vision and see the future, but for them it's very difficult. So actually I cannot answer this question. This requires more research, but not only from a technological point of view, but a research that also includes philosophers, ethnographers, a broader transdisciplinary group of people who come together in order to figure it out how to do this transition. So, do you see this more clearer than me?
No, I agree with this. And I think as of now, there is still a role for the therapist. There are lots of things that robots are great at, but identifying a good movement is something that we're still much better at. I mean, we can see somebody walking and we know that they're happy. And this is something that we haven't been able to quantify and to translate to our robots quite as easily. And so we still need the expertise from the therapist to identify when that movement is correct and not maybe training some bad compensatory movement. I mean, you see this with people who do yoga at home. So they can do their yoga moves, but if they don't have someone there to guide them and tell them when they're doing something that could hurt them, then they could get injured. And so at an immediate level, we could have something like a tele-rehabilitation type of framework, but I agree with Laura that I think shifting this expertise to understanding the robots and how to get the most out of them is the best way forward towards working with these therapists.
Yeah, that said, our goal is not to replace therapists. I don't think the humans can be replaced. There is something in us, right? The companion, the understanding, the empathy. So once again, a case, my mother goes to therapy, and she's a very talkative person. She likes to talk a lot, and she looks forward to go to therapy just to talk with a therapist, right? So it's not that she's looking forward to do the exercises, that yes, she spends 25, 40 minutes talking to somebody. You don't need to do this in the clinic, right? So you can do this remotely, and there are other ways of communicating in the distance, as we discovered with the pandemic. So, yeah, not replacement, but it's just a change of roles, keeping and maximizing the humanity of the therapist.
Yeah, and then the therapist's time goes further, right?
Exactly.
Okay, well, thank you very much for joining us. Please join me in thanking the presenters and panelists one more time. And we'll adjourn. Actually, Katie, could you advance the one slide, please? We have one final SHErobots coming up on the 21st of this month. And we'll actually, if you're interested in the medical robotics, they'll still have some application, because we'll be talking about soft robotics, soft medical robotics, and then also actually soft maritime robotics with two prestigious faculty at the TU. So please mark your agendas and come join us for that. And then stick around, because you can interact with the demos. So once again, thank you for your time and joining us and making this program successful. All right.
Thank you.